Hi all, today we discuss the last theorem of chapter 9, that is Weingarten map is self-adjoint. Self-adjoint means we already you might have seen this formula in your functional analysis classes. This will give the property of self-adjoint operator. The adjoint is defined using some kind of inner product. We are considering here is Rn, therefore we have usual inner product. Dot product can be considered as usual inner product, and we have already seen that this is the Ax comma y equal to x comma by. This is the definition of the adjoint of this A, satisfying the operator satisfying this condition for all x and y. Then this B is called the adjoint of A. Self adjoint means this B and this A will be the same. So we have Ax y should be same as x comma ay for self adjoint operators. Here this inner product is dot product itself, so we write x dot y is equal to x dot ay. So this is the definition of self adjoint operator in case of the dot product or inner product as the dot product. Now if we replace this A by LP, you can get this equation. So LP x dot y is equal to x dot LPy. So that is what you have to prove in this theorem. LPV dot W is equal to V dot LPW. So we start evaluating LPV dot W by assuming that this f is a function from U to R, and we use this f to define this S is equal to f inverse of C for some C belongs to R. Anyway, and we also defined or assume the normal vector field n of p. N of p is nothing but del f of p by setting these two L of n del f of p by the norm of del f of p, norm of del f of p. So this will give one of the normal vector fields for all p belongs to S. So by setting these two quantities, you start evaluating this LPV dot W. So by definition, this is equal to LPV is equal to minus del V n dot W, that is equal to minus del V of this n is del F divided by norm del F. So this is the normal vector field dot W. Now you write this is equal to minus of, we have minus of using the product formula, we have this is a del V of 1 by norm del F, this is 1 by norm del F times del F of P plus 1 by norm del F of P. This norm del F of P is considered as the scalar function. Del V, this is del V of del F. Okay, dot W. That means we apply this del V to this vector field. That means del F is a vector field, and 1 by mod del F is a scalar function. Then this is the scalar into a vector field. So using the product rule, you can get this one. Okay, del V of the scalar times this this del F P and 1 by the scalar times del V of the vector fields. So when you evaluate this, you can get that is equal to minus del V this 1 by norm del F del Fp. So this is 1 by norm del F del Fp dot W. W is here, so we can distribute this dot product to this, and we have we also distribute this minus sign, so we have minus here, and that will be 1 by norm del F of P, norm del F of P times del V of del F, del V of del F dot W. So when you distribute minus and w or the distribute dot product and minus together, we can get this one. Okay, now we know that this del f of p dot w is equal to 0, because this del of p is always perpendicular to p, and this w comes from the tangent space. So using this, since we have this result, we can get the first term as 0, then the remaining will be so this can be written as this is equal to this LPV, that is LPV dot w can be written as minus of 1 by norm del f p del f times del v of del f dot w. So this is the left hand side LPV dot w. Okay, now we simplify this, that is equal to which this can be written as minus 1 by norm del f, this is norm del f times, we write this as p comma del v of, we need to find out this del f. We know that del f assigns the vector at p as dou f by dou x1 etc, dou f by dou xn plus 1. Okay, now we have to evaluate del v of this. Del v of this means we need to find out del v of each of the components. So we need to find out the del v of this component first, then the second, so that will give this del v del f. Okay, so we write that is equal to, so this quantity can be written as del v of this dou f by dou x1 at p. Okay, so this is the del v of the first component and etc. So del v of del f is obtained by taking the del v of each of the components dot this dot v. This is the this is in fact first of all we write that is equal to del v of p and all the way up to del v of the last term will be del v of dou f by dou xn plus 1. Okay, dot this dot w. Okay, now we evaluate this del v of del f del v of dou f by dou x1 at p, so which is equal to minus 1 by norm del f. Okay, now this is p comma and del v of this quantity can be evaluated using del v of dou f by dou x1 dot v. Okay, this, of course this is at p and the final component will be a del of dou f by dou xn plus 1 at p dot again v, this is v and we have w. Okay, now you can write it as minus 1 by a norm del f of p. Here we have p also, all these terms we have p, we are evaluating all this at p. So this is p comma, first of all we need to take the dot product of this. This dot product can be written as summation I is equal to 1 to n plus 1 dou square f by dou xi x1 at p into time this times vi. When you expand this you can get we know that this del of dou f by dou x1 is this dou by dou x1 of dou f by dou x1, dou by dou x2 of dou f by dou x1, dou square f by dou x dou square f by dou x3 dou x1 etc. So we write that as that so for the first quantity we write the dot product of the vectors. The first term will be the first vector will be at the point p, we have dou f by dou square f by dou x1 dou square f by dou x2 dou x1. That means the derivative of dou f by dou x1 with respect to x1 with respect to x2 etc. Okay, so this is the first vector and the second vector will be w. Second vector will be this v, that is v1 etc vn plus 1. Okay, Okay, so we have to at the point P. So we have for this dot product we collect dou square f by dou x1 into v1, dou square f by dou x2 into v2 and all. So the first term will be, the first quantity will be this sum. Okay, so this is obtained. This dot product can be obtained by expanding the summation. The second will be the summation I equal to 1 to n plus 1 dou square f by dou xi dou x2 for the second component. That means all these points we have x2 here. Okay, so times at point P times vi again. Okay, now the last term will be summation I equal to 1 to n plus 1 dou square f by dou xi dou xn plus 1 at the point P times vi. Okay, so this constitute this vector dot we have w. Okay, now we write this is equal to minus 1 by norm of del f of p. This is norm del f of p. Summation, we write it as a summation j is equal to that means we have two again we have a dot product here, dot product of this vector dot this vector with w. That means we have in w we have w1 w2 etc wj, then wn plus 1, then we need to take the dot product of this. That means this times w1 plus this times w2 plus and so on. Okay, so we write this is equal to I j is equal to n plus 1. That means this in fact this is these are two summations. One summation is for I and then next is for j, both varies over 1 to n plus 1, and we write this is equal to dou square f by dou xi dou xj, and we have vi is here times wj. Okay, so this will give this LPV. This is the left hand side. What is the left hand side? Left hand side is LPV dot w. The similar fashion we will evaluate LPW dot v. Okay, that means the right hand side should be v dot lp w dot v dot lpw. So in order to find out v dot lpw, it is enough to show that lpw dot v will also give the same formula. Okay, so next we will evaluate that one. When you evaluate the same quantity lpw dot v with the same rules what we have followed just before, you can get this is equal to minus 1 by norm del f of p summation I comma j from 1 to n plus 1. Here we have dou square f divided by dou xi dou xj at p wi into vj. This is the only difference. Okay, so we have already proved that lpv dot w is equal to minus 1 by norm del f of p summation I comma j is equal to 1 to n plus 1. This dou square f by dou xi dou xj at p, this was vi into wj. So these are the only difference, but we know that dou square f by dou xi dou xj is same as dou square f by dou xj dou xi. Okay, for every I and j, because this f is a smooth function, to define that surface, then we can get this equality. Then we write this we start with lpv dot w is equal to minus 1 by norm del f of p summation. We have two summations I comma j, both summations start from 1 to n plus 1, and we have dou square f by dou xi dou xj of p This is Vi Wj. So this is the first definition, first equation. So that is equal to minus 1 by del f of p, norm of that, norm del f of p. This is summation I comma j is equal to 1 to n plus 1. We write this as dou square f by dou xj dou xi, because both are same, of p Vi Wj. You write it as same as that. That is equal to minus 1 by norm del f of p summation I comma j is equal to 1 to n. This is dou square f by dou xj dou xi of p. This can be written as wj and vi. This is vi here. So that is equal to this can be written as you can interchange this sum. This is from 1 to n plus 1. You can change this the summation, order of the summation. So if you in this equation, if you write this j is equal to 1 to n plus 1 is the inner summation, then you can interchange both, because it contains only a finite number of elements. So the interchange of the summation will not cause any change in this equation. So now you can consider the ij, instead of ij we can consider ji. Both will give, this will be ji, both will give the same thing. Then you can consider this thing as lp w dot v. Okay, so this shows that lp v dot w is equal to lp w dot v. That means LP is self-adjoint. Okay, self-adjoint. With this we can conclude chapter 9. The next class we will discuss chapter 10.